let's begin our discussion of the correctness of this algorithm and this data structure. So we're going to begin by a question, which is if we have a tree of height h and a leaf x, how many nodes are on that path? And then we're also going to answer how many nodes of each color can be on that path. So if I have a red-black tree, I'll try and draw it in a reasonable way. We have some path going through the tree. Who knows what it does? Some of the nodes will be red. The question is, how many of those nodes can there be? Well, because it's height h, there's at most h nodes. And if there's at most h nodes, how many could I possibly make red? Well, I can't have 3 red nodes in a row, or 2 red nodes in a row, and the root had to be black. So the worst I could possibly do would be something like this, if I'm trying to be the devil's advocate here and say what's the most number of red nodes. And that looks like about half. In fact, if I had one more child, it would be exactly half. So it's about h over 2 is the most number of red nodes I can have, which means I must have always at least h over 2 black nodes. So we have h over 2 red at most, and h over 2 black at least. So with this data structure, we have an upper bound on the number of red nodes and a lower bound on the number of black nodes. We're going to use this fact extensively, and I've included a proof of it in Lemma 1. It is at the end of these notes. If you want to look at that yourself and see a formal proof of what is the maximum number of nodes I can have in a red-black tree. Notice I didn't count the leaves here because it was a bit tedious to do that. And we're going to actually get rid of them in our analysis when we do our proof anyway. So it's not going to matter too much. Now, let us examine the theorem we have, and we will then come back and prove it in a second afterwards. So our primary theorem is that a red-black tree with n internal nodes, remember the only leaves are nil. So internal nodes refers to every single node that stores data in our data structure, and then the leaves are all of these nil pointers. So if we have n internal nodes, the height is at most 2 log base 2 of n plus 1. This is a good bound for the height and is similar to our complete binary tree stuff. So let's look at our complete binary tree theorem that we had before. I've just typed up the proof here. We did this already, and I explained it when we did both binary search trees and heaps. So we've seen this exact theorem and a proof of it several times. I just haven't worded it in that way. So here I say a complete binary search tree of height h has 2 to the h plus 1 minus 1 nodes. We don't really need to go through the proof of this. We've done this already. The important thing is that we have a characterization of the number of nodes in terms of the height, and then maybe later we'll come back and talk about how the height relates to the number of nodes as well in this more logarithmic sense. So here we have the theorem. I could read this to you and I could try to recreate it, but for many people reading this theorem, it won't be that helpful. I will talk about the details in the theorem and reference them in a picture. So I will talk through this a little bit, and I will try and describe everything in terms of a picture that I have down here and explain why this works and what the reasoning behind it is. So we have a red-black tree. Step 1 of the proof, and you should do this in all proofs, is define the variables you're going to be using. So I'm going to let t be a red-black tree of height h. Similar to when you're programming, you don't want to have variables introduced in your proof that you have not defined in the program. You'll get your sort of variable undefined errors or variable not defined in scope or whatever. Same exact thing when doing proofs. We're immediately going to remove all of those nil leaves. So we're going to say let t prime be the tree formed by removing all of the leaves from t. This is the act of cutting off the nil nodes. And if you look at my little picture here, I didn't draw in all of these nil nodes that I could have drawn in because they're really tedious. So we've already done that in our picture. Then what are we saying? We're going to look at the number of red and black nodes like we did in our previous example. So looking at this tree, what is the most number of red nodes I could have? Looking at it, I can actually find a path that satisfies that. This path going from 26 to 17 to 14 to 10 to 7 to 3 every single other node is red. And we already talked about that is the maximum number of red nodes I could have. So the most number of red nodes is going to be about h over 2. And then therefore we must have at least h over 2 black nodes. There is no way around that in this tree because we cannot include any more red nodes along a particular path because every single red node must have both of its descendants being black. So there's no way around this. So the important thing is the number of red nodes is at most h over 2, and the number of black nodes is at least h over 2. And we're going to use that number of black nodes is at least h over 2 in our proof. In practice, actually, this number of red nodes is h over 2 rounded down, and this is h over 2 rounded up. But that's a bit tedious to deal with, so I'm not going to write that here. In the actual proof of the theorem, you'll notice I include that detail of the rounding down part, just for the specifics of what I need to do. So we have that we know that there is at least h over 2 black nodes in this path. And remember, every single path must have the same number of black nodes. Therefore, every single path, no matter what I choose, must have at least h over 2 black nodes in it. So we are going to use that fact in our theorem, since every path from the R to a leaf has the same number of black nodes, like I just said. Every path from R to a leaf has at least h over 2 black nodes. And again, that number could be much larger. It could go all the way up to h in a complete binary tree. If you had a complete binary tree, you can color the entire tree black, and that you could have up to h nodes that are all black in the same path. But it's at least h over 2. That's the important part. Looking at our tree, this guarantees, no matter what, that I have a binary tree that is complete as a subtree of this tree. If I was to cut this tree off at that height over 2, so in this case the tree has height 5, and if I was to cut this off at h over 2, then I would have a complete binary tree inside of my red-black tree. So I'm cutting this off. Remember, this tree had a height of 6. Why did it have a height of 6? Because you might look at this and go, it has 1, 2, 3, 4, 5, but I'm not counting the nil nodes. This actually has a height of 1, 2, 3, 4, 5, 6. Which means that this tree here corresponds to that t prime, which has height h minus 1. And if I cut this off at h over 2, h over 2 is going to be a tree of height 3. Oh no, we've made an error. Let's fix this and change this from h over 2 we're going to cut it off at to h over 2 minus 1. Again, because we are cutting off all of those leaves, we need to be a bit cautious about how we handle these values. So we have a binary search tree of height 6 over 2 minus 1, which is height 2, guaranteed to be within this tree. And we can see that inside of here there are some paths which have 3 black nodes, some paths which have 2 black nodes, some paths which have 2. It doesn't really matter for those, but there is a complete binary search tree, this tree here, that is a subtree of our red-black tree. And that's the last fact that we need, because the number of nodes in that tree, I have a theorem for that. That is a complete binary tree. Therefore, the number of nodes in this tree, which will be 2 to the h over 2 minus 1 plus 1. Why is it that? Well, we have a theorem for that. That was theorem 2 for the number of nodes appearing in a complete binary search tree. So this equals 2 to the h over 2. That is the number of nodes in this complete tree. And there are more nodes than that, but this will give me a bound on the number of nodes because I have at least this many, n is greater than or equal to 2 to the h over 2. And we can then solve that for our height. So let's see how we do that. Let's finally look at the end of the theorem. By theorem 2, T prime contains a complete binary search tree of height h over 2 minus 1. We have that, and again, I'm rounding up because of a technicality. If you want to see the details of that, it is in lemma 1 again at the end. And if you like proofs, it's definitely worth looking at that. That's a very fundamental proof I did for you, and you can hopefully understand the details there. Now, by theorem 2 is this guy, about complete binary search trees, I know T prime has at least as many nodes as that subtree that I found, and therefore T has at least that many nodes as well. Because I had cut off the leaves, and after I re-add the leaves to the problem, all of those values like 3 that looked like leaves before are now internal nodes because they have 2 nil pointers at them. Therefore, T has at least however many nodes we computed from our formula, internal nodes. And that looks like, in some sense, the convenient bound we had up here that we could then rearrange and solve for stuff. So this theorem is really where all of the work is done. What we have is, because of this balancing act between red and black nodes, we guaranteed have at least a reasonably sized complete binary search tree as a subtree of our tree. That is what this theorem is doing. That's how this red-black tree balancing will work for keeping our data structure at a reasonable size. Now let's bring it all together with proving our theorem. It takes one line at this point. We're going to let T be a red-black tree. And then by the theorem we had, the number of nodes n is greater than or equal to that number of things we found in the problem. And we just rearrange it and solve. So all of this is just the algebra for getting there. And then we have that the height is bounded above by 2 log base 2 of n plus 1. Hey, and conveniently, we actually know the height is bounded below by the height of a binary search tree that is complete. So the height is bounded below by log of n and bounded above by log of n. So the height is in theta of log of n. Therefore, if any algorithm we look at is in theta of h, it will also be in theta of log of n. And that is our important thing. The height of this tree is at most twice log of n. Ignoring the plus 1 for a bit of convenience, that is a upper bound on the height of this binary search tree for a red-black tree. And therefore, this will guarantee that as long as making it a red-black tree isn't too costly, our algorithms will run well. So the next thing is going to be, how can we actually implement our methods to guarantee that we keep a red-black tree when we're analyzing this stuff?